This video is on wave motion. I will be able to understand the motion of waves. We're going to take notes from a video, discuss with group members, observe a demonstration, and work with a partner in an observation experiment. So first we have mechanical waves. A mechanical wave is a physical disturbance in an elastic medium. So consider a stone dropped into a lake. So here's our stone dropped in it, and then you see the ripples going towards the other side. Energy is transferred from stone to the floating log, but only the disturbance travels. Actual motion of any individual water particle is small, so energy propagation via such a disturbance is known as mechanical wave motion. So we have transverse wave. The vibration of the individual particles of the medium is perpendicular to the direction of wave propagation. So we have the motion of the wave going towards this block on the end, and if you see the hand, it's going up and down, so it's creating waves, a wave up top, and underneath, it should show underneath, but up and down going towards there. So it is perpendicular to the direction of the motion of the wave. Next we have longitudinal waves. In a longitudinal wave, the vibration of the individual particles is parallel to the direction of wave propagation. So if the motion of wave is going this way, that means the waves are going to go in a direction that is parallel to the direction. So if it's going this way, that means the motion of particles is going back and forth in the same line. So water waves. An ocean wave is a combination of transverse and longitudinal waves. The individual particles move in ellipses as the wave disturbance moves towards the shore. So here we can see the wave, it's going to crest and then eventually it will fall, so there is the ellipse that is created. Periodic wave motion. A vibrating metal plate produces a transverse continuous wave as shown. For one complete vibration, the wave moves a distance of one wavelength as illustrated. So if we pick one spot on a wave and we measure to the next spot on the next wave, that is one wavelength. So it's the distance between two particles that are in phase. So typically we either go at the crest at the top and the crest, or we go trough to measure the wavelength. So how do we find velocity and wave frequency? Well, the period t is the time to move a distance of one wavelength. So velocity equals wavelength over the period, but we already know that t, or the period, is 1 over the frequency. So we get velocity equals frequency times wavelength. And yes, we need to understand the units. These are in hertz. So how do we produce a longitudinal wave? An oscillating pendulum produces condensations and rarefactions that travel down the spring. The wavelength L is the distance between adjacent condensations or rarefactions. So here we have an electromagnetic vibrator sends waves down a string. The vibrator makes 600 complete cycles in 5 seconds. For one complete vibration, the wave moves a distance of 20 centimeters. What are the frequency, wavelength, and velocity of the wave? So frequency, we have 600 cycles in 5 seconds, so that's 120 hertz. The distance moved during the time of one cycle is the wavelength, therefore 0.02 meters. I don't know if that's correct though. So let's check again. So 20 centimeters, and we need to go back 2 to make meters. 1, 2. Should be 0.2 meters. This is a mistake. So V equals frequency times wavelength. So putting in the numbers, we do have the frequency, we have the wavelength, although it is the incorrect wavelength. This should be 2.4, should be a slightly bigger number than 2.4. The superposition principle. When two or more waves exist in the same medium, each wave moves as though the other were absent. So the resultant displacement of these waves at any point is the algebraic sum wave of the two displacements. So what happens is, if, like on a trampoline, if you guys do a double jump, you can get someone going higher because you're using the energy of both. So we have constructing interference where the waves are happening at the same time, so you get a resultant higher wave if you put them together. And the same thing, if you have a trough at the same time a crest is going, it lowers the resultant wave. So, formation of a standing wave, go ahead and draw these in. And also you're going to do the possible wavelengths for standing waves. Go ahead and draw these as well, I'm sorry. And you're going to do the same thing for the possible frequencies. Understanding that frequency equals velocity over the wavelength. And that's it. So we'll be doing some experiments to look at waves, and joy, joy, joy. Shout out to Carlos. Shout out to Jackie, because they were in the last video, but I redid it because it sucked. Lates.